I'm not even on meds right now. Scurv catching. Curve sketching. When it comes to curve sketching, I think we've already illustrated this semester that we can use the computer to do a lot of this, but sometimes the computer misses some of the details that we can get by doing the calculus. So really, this whole topic is a little, you could argue, a little bit outdated. But if you want to look at it from a different perspective, look at it like, can you handle a problem that takes you 35 to 40 minutes to do? Like, can you actually organize your thoughts and keep it all together? You know what I'm saying? Like, can you do a process that is this long and involved? That's really what this is about. So we want to sketch a graph of some arbitrary function, and the key word there being arbitrary. In college algebra and in pre-cal, we kept ourselves, we restricted what we were able to graph into certain categories, quadratics, polynomials, trig functions, exponential, log. But now we just go for just any function. Just can we graph it? And we're going to use a process. So this is a 9-step process. The book, I think, has a process that's a little bit more involved. And let me just say that some of these, you don't have to do each of these steps. But each of these steps could be helpful when you're trying to put the graph together. So the first thing we'll do is we'll look at the function, we'll find its domain. Make sure we understand the things that can and cannot be plugged into the function. We'll try and find the x and y intercepts. That's something we did in college algebra. Do you remember how to find the x-intercepts of a function? Set it equal to 0.
And then set the equation equal to 0. Find your x's.
Okay, so that's how you find the x-intercepts. You set the function equal to 0. How do you find the y-intercepts? Plug 0 in for x into the function, see what it spits out. Okay? Checking for symmetry. What is that? So that has to do with this idea of even and odd functions and whether or not f of x equals f of negative x. That's what we call an even function. Or whether or not negative f of x equals f of negative x. That's an odd function. So we can check, and we'll go through an example and we'll see, okay, whether or not a function is even or odd. That just helps us know whether or not, like, if we graph half of it, the other half will just be a reflection of it on the other side of the y-axis. Right? So things like that can just help us. We will find asymptotes. So we have two types of asymptotes, don't we? Whenever we do have them, we have, well, there's actually, you could argue, 3. There's your vertical, your horizontal, and then sometimes the oblique are called slant asymptotes. I'm only going to work on the vertical and horizontal asymptotes. So let's just verbally talk about them. You have a function will have vertical asymptotes wherever the denominator is 0 and the numerator is not. Okay, that will give you a vertical asymptote. Now, the horizontal asymptotes are the end behavior of your function. You have to figure out what's happening at the ends. And to do that, we will use calculus. We will take a limit as x goes to infinity to figure out what happens to the right, and x goes to negative infinity to figure out what happens to the left. Okay, that'll give us our end behavior of our function. So we'll do that. Then we'll determine where the function's increasing and decreasing and constant. So we've done this, right? That's where you take the derivative, you set it equal to 0, you do a number line, you partition it, test points up, down, you figure out where the function's going up and down, right? Okay, so we've done that. We'll find any local maximums and minimum values and where they occur, so we've done that. And then we'll determine where the function f is concave up and down, also determine inflection points. So we've done that. That's second derivative, right? Then what we're going to do is we're going to make a table. And we have not done this yet. We have never done this part. And then once we have our table, we are going to sketch. And we're going to call this table the Bobby method. And this is because this guy, when I first started teaching calculus, I was showing this method, and it was kind of a method that I had come up with myself because I didn't like the book's explanation. and this student that I had didn't like me. And I told them at the beginning of the semester that my name was Robert. They could call me Robert or Rob, or they could call me Mr. D, whatever. And I said, don't call me Bob, though. I don't go by Bob. So he came up and was like, yeah, so your little Bobby method, you know. And anyway, so I've stuck with it this whole time. So we're going to call it the Bobby method. All right. Where's my little rag? But it'll stick. You'll remember it more that way. Where's my? Do y'all see the yellow rag around here?
Maybe it's behind your big board. Behind that board.
No, it's not. I might have to use a real eraser this time. Okay. Yeah, if you don't mind, because this thing is just going to make a mess, I think. Yeah, this doesn't do anything. Just smears it. Yeah, that doesn't do anything. All right, so let me grab a function. And so you tell me. I mean, I guess when I give you demonstrations here, I can kind of choose like the level of the problem here. You want to start with something extremely like basic? You want to start there? Yeah, okay. All right. Yeah, let's graph a line. All right, let's start with something kind of basic. Come on. That'll work. Thank you. Where'd you get it from? Across?
The tutoring lab.
The tutoring lab had it? Okay. All right, so I don't have that 10-step process with me unless I have my notes here. I did not bring the notes. Okay, so someone can help me. We can refer back to them if we need. All right, let's get our function. Now I'm just going to go into the book here, and I'm going to pick one of these first problems here. And I kind of don't want to do a polynomial because you've already taken college algebra, but we'll do one. All right, x to the fourth minus 8x squared plus 8. All right, so our goal is to sketch that. Now do kind of keep in mind, like there was a time when we didn't have computers, right? And we couldn't just go into the website and graph something. That wasn't too long ago. You know, I mean, like, when I was a student in calculus, I couldn't just, like, I don't even know if Google was really even that robust yet, where I could go there. You had to, like, use a mathematical program. All right, first step, let's do the domain. So when we talk about the domain of this function, well, it's a polynomial, right? And therefore, you can plug anything you want into that. So our graph is going to exist everywhere. Our domain is negative infinity to infinity. So we keep that in mind when we graph it. It's going to go both directions forever, right? No holes, no breaks. Step 2. What was step 2? X and Y intercepts. All right, so let's go for the x-intercepts. So for the x-intercepts, I set the function equal to 0. And when you get to this step, you want to try and do this, okay? But there are going to be some functions where you will not be able to actually get this, like that the equation will be just something beyond what you can do. Now, maybe you could do it using Newton's method, but if it can't be done by hand, we'll just kind of skip it. This one looks like we might be able to do it by hand because that looks like a quadratic type equation. It almost looks quadratic. So it should factor out. Let's see, does it though? It doesn't, right? So what could we maybe try? Like a quadratic formula? So really what I'm doing is I'm saying, look, everywhere I see x squared, I'm replacing it with u. And then this equation is really going to turn into u squared minus 8u plus 8 equals 0. That's kind of a technique that you use in college algebra, substitution technique. And then I can use a quadratic formula here. So what I'll say is u is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Does this look okay to you? All right, so we get 8 plus or minus square root of 64 minus 32 is 32 over 2. And let's go ahead and break out our calculators. We'll get decimal approximations to this. Whoa, whoa. All right, so I'm going to do square root of 32. So I'm getting 8 plus or minus, let's go with 5.7. I'm going to round just one decimal place over 2. Everyone okay with this? And now I'm going to get two answers from this. 8 plus that 5.7, then divide by 2. So 6.85 is one solution. And then 8 minus 5.7 divided by 2. The other one is 1.15. So u is equal to this, right? One of those two. Everyone okay? Now, you have to remember here, what was u?
X squared.
U is x squared, wasn't it? So this is actually saying x squared is 6.85, and it's also saying x squared is 1.15. So now you have to take the square root on both sides, and you have to do plus or minus on each of those. I'm going to have 4 solutions. So I get x is plus or minus 2.6, and I do the square root of 1.15. X is equal to, I'm going to say 1.1. I know it's not, it's like 1.07, but good enough? Oh, plus or minus. So I wound up not factoring. I wound up just rewriting it as a quadratic using quadratic equation, getting 2 solutions, and then replacing u with x squared plus or minus roots. We're good? Okay. All right, so this is going to be off camera, but I'm going to start putting this information here. So domain, I think I'll write the domain different notation. That's all real numbers. And then my x-intercepts, I have 4 of them. They are plus or minus 2.6 and plus or minus 1.1. How about the y-intercepts? Y-intercepts should be easy. Just plug 0 into the function. Right? Just plug. By the way, this was y equals, right? But I'm really looking at this like f of x, right? Okay, so plug in 0, which means go f of 0, and you get 8. All right, we good? All right, let's go to step 3. Step 3 is what? Symmetry. All right, so when we do symmetry, I'll do it over here. All right. For symmetry, let me first check. Is f of x equal to f of negative x? If so, it would be an even function. All right? And let's check it. So f of x is just the function itself, x to the 4th minus 8x squared plus 8. Is that equal to, this is a question, right? Is that equal to f of negative x? So if you plug in negative x, you're going to have negative x to the 4th minus 8 times negative x squared plus 8. And the thing to note here is that if you have a negative number and you raise it to the 4th power, it's going to be positive, right? So this is really just x to the 4th, and this right here, same thing, negative x squared. So you get minus 8x squared again plus 8. So they are the same, right? These are the same functions. So check, which means it's even. Now, what does it being even mean? Yeah, I mean, it is even. Now, oh, by the way, a function can a function is either even or odd or neither. You can't be even and odd at the same time.
What does neither look like? Just one fact.
What's that?
What does neither look like?
Neither is the exponential function. Let me first talk about even. An example of an even function, is the cosine function. It's an even function. So if you graph it, it looks like this, doesn't it? But if you reflect that over the y-axis, right? If you reflect this over the y-axis, then it lands right on top of itself. So the cosine function is a reflection of itself over the y-axis. That's what it means to be even, a reflection over the y-axis. Okay, so that's an example of even. An example of an odd function. Let me give you another even one. X squared. Duh. I mean, it's even. Power. The power is even, right? Reflect. Okay. So an example of an odd, sine x. This is an example of an odd. And sine looks like this. Goes like that, right? And then the back goes like this. So do you see it's not a reflection over the y-axis? It's actually a reflection over the y followed by a reflection over the x. So it's like a double reflection. Got it? Goes this way. So if I reflect that, it would have looked like this if I reflected it over the y. And then if I take that and flip that over the x, I get the dotted one.
So it's a mustache.
So it is a mustache, yes. So this is odd. Make sense? Another example of an odd, x cubed, right? That's an odd power. X cubed looks like this. So if you take this piece and flip it, and then flip it down, it lands on top of itself. You could also do this piece this way and then up, and it would land on itself. All right, neither, an example of neither, okay? An example of neither one would be like e to the x. Because, like, if we flip it over the y-axis, it doesn't land on itself. If we double flip it, it doesn't. So there's a lot of neithers out there.
Yes.
Even and odd is kind of a special category. Okay, so we have an even function. That means we don't need to check it to see if it's odd because it can't be odd and even at the same time. And so we move on. What's the next step? Asymptotes. So 3, we're even. So the fourth step. All right, let's talk about vertical first. So with vertical, what I'm trying to figure out is, do we ever have fixed over 0? Like, is there any number I can plug in that's going to give me a number on top and then give me 0 on the bottom? Well, I don't even have a fraction, right? So this isn't going to happen. All right, so there's no vertical asymptotes. What if there was? I would have to do a limit as x approached that number from the left into the right and to see what's happening, okay? But this was a basic example to start, so, okay, horizontal. So to do this, I need to actually do two things. The limit as x goes to infinity of the function, and then the limit as x goes to negative infinity of the function. So do you all understand that this limit means you're going to go and look at what happens to the function as you go out to the right, and this is saying what happens as you go out to the left forever. Yes? All right, so let's do this. Limit x goes to positive infinity of x to the fourth minus 8x squared plus 8. What happens there? You have infinity to the fourth power, which is still infinite, right? Minus 8 times infinity squared. So you think this is going to overwhelm this? We talked about this already, right? It will. And then 8 doesn't matter. Now, if I wanted to show that more mathematically, that it will overwhelm it, just watch what I do here. Is that not the same expression? All I did was pulled an x squared out of just these two. So I pulled an x squared. If I distribute that through, I get x to the fourth minus 8x squared, which is the same expression. Yes? OK. This right here is going to infinity. Times, this is going to what? Infinity minus 8, that's infinity. So you have infinity times infinity, which is infinity plus 8. So that's infinite. Yes? So this is headed to infinity. What does that mean with my graph?
That on that side of the x-axis, you have the positive one.
OK, so as x goes to infinity, as I'm going out to the right, my function is headed to positive infinity. So my graph should do something like that on the right. OK? Now let's go to negative infinity. So what changes here?
You're going to get a positive.
The fact that I'm going to plug a negative number in here means nothing, because remember, this is an even function. So whatever happens on this side is going to be a reflection on the other side. So I mean, this is also going to go to infinity, isn't it? So I know that my two sides are going to go like this, which in college algebra, you should have been able to tell me that already, because you were taught in college algebra that if this was an even power, and if this was the leading coefficient was positive, which it is a 1, that the end behavior is this. You know, if this had been odd, then it would be either like this or like this, depending on the leading coefficient. So, I mean, yes, we could have answered that a long time ago, but in general, for arbitrary functions, you have to go through this process. All right, look, we're almost halfway through the steps. Step 5. All right, we want to know where this function is going up and down. All right, so let's do this. 5th step. All right, so I need the derivative, don't I? 4x to the 3rd minus 16x. That's our derivative, and we will do what with this? Set it to 0. So if I set that equal to 0, we get 4x cubed minus 16x equals 0. And how would you solve that? Take out a 4x. What else? You see something else there? X squared minus 4 is the difference of squares. So x plus 2x minus 2. So we have how many solutions there? 3 of them. So x is 0 and positive and negative 2. Now we have to figure out where the derivative is undefined, or where the derivative does not exist. Is that happening at all? No, our derivative is very nice, isn't it? It's never division by 0 or anything like that, but we do need to consider it. Again, when the functions become more complicated, we may get some critical numbers from this. So this is not happening because it's a polynomial. So now what we do is we do our number line. We plot our critical numbers. That breaks up our number line into these pieces, and then we pick test points, right? And the test points we pick are here, 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 here. So maybe like -3, -1, 1, and 3. And then you plug those where?
Into the derivative.
Derivative. Into these test points are going into the derivative because we're trying to figure out if we're going up or down. The derivative, the sign of the derivative tells us whether or not we're going up or down. So check out my derivative here. I'm going to just take this derivative real quick. I'm going to factor it up here. Right, that's the factored form. That's not squared. That's the factored form of the derivative right there. I think it'll be easier for me to plug in the numbers if I do it that way. So take a -3, I'm going to get negative here, right? Negative 3 here, I'm going to get negative. Negative 3 here, negative. So I'm going to have negative, 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 which multiplies to be negative. So that means my function is going down here. I'm doing this mentally without actually plugging them in. Is that all right with you? You understand what you would have to do if you didn't want to do it this way, right? Just plug them into negative 1. I would get a negative, positive, negative. So negative, positive, negative, which is going to turn out to be positive. So f is going up here. All right, now plug in 1. So positive, positive, negative, which means negative. So it's going down. And if we plug in 3, it'll go up, okay? All right, that's what the function does. It goes down, then up, then down, then up. Step 6, local max, local min. Where are our local maxes? We only have one, right?
0.
At 0. So it's at f of 0, and it is what? 8. Hey, isn't that the y-intercept? The y-intercept is a local maximum. All right, well, local minimums. I actually have 2 of them, f of negative 2 and f of positive 2. Right, these two are minimums because it goes down then up, down then up. And let's plug those into the original function. We should get the same value for both of these, shouldn't we? Because it's an even function, so if you plug in a negative 2, it's the same as plugging in positive 2. Let's just plug those in. I believe, let's see, 416 in there, minus 8 times 4, plus 8, negative 8? No. Yeah? Negative 8.
Yeah.
Negative 8. So both of these give you negative 8. Now, it may not seem like we need this information to graph it, but I mean, this is going to become useful later. We're going to actually just plot points. All right. That's 5 and 6. Are we on to 7 now? 7 is concave up, down?
Yep.
Yes? OK, so step number 7 is to take the second derivative and do basically the same exact thing we just did. So my second derivative is 12x squared minus 16. And then we'll set that equal to 0. And you can pull a 4 out. I'm gonna divide by 4. Is that allowed? I can divide by 4 because it's an equation. I have 0 on the other side. And move the 4 over. And divide by 3. So x squared is 4/3. And so x is plus or minus root 4/3, which is the same as 2 over root 3, which is the same as 2 root 3 over 3. Any of these answers, I don't care which of these you use, okay? You can do the root on top and bottom, that gets you here, and this is rationalizing the denominator, but it's not necessary. Now, I'm going to put those on a number line, right? I have a positive and a negative number. Now, later on, we might need to know exactly where these are. So let's go ahead and get these as decimals. I'm going to do 4/3, and I'm going to take the square root. (1.15-ish). So this is approximately plus or minus 1.15-ish. Keeping that in mind for later. Does the second derivative ever not exist? No, it's fine. It's a polynomial. So now I do a number line. Root 4/3 here. Negative root, 4/3 there. Test, test, test. So this is where knowing the decimal helps, because 1.15, that's negative 1.15. That means you can pick like negative 2. It would be fine. Negative 2 here. 0 is a good one here. And 2. And where are these going? Into the second derivative. Go ahead and plug those in real quick. I'm going to get a tissue. I'll be right back. Talking about the test earlier, is that sometimes I feel as if the grades do not reflect what you're capable of. Meaning that, I mean, I think for some students, you know, the grade is an exact reflection of the fact that they're not putting in enough work. But there are also as many students who are doing their homework, are trying, are putting the effort, and they sit down, they take the test, and it just does not come across. And I really need to make this part of my goal as doing this for a living. I need to find a way to help students become better test takers. So I'm really going to make that a focus for myself, like a goal, like maybe a 5-year plan here of like trying to help students somehow become better test takers and helping them throughout the semester become better test takers. Because I hear it all the time. It's like, oh, I get to the test, I freak out. And so, I mean, imagine if we came in here and every single day we spent 30 minutes and I gave you 2 or 3 problems and you had to take it like a test every single day, right? I mean, by the time we got to the test, you would probably be pretty comfortable with me coming in here and giving you an hour, 40-minute test because you've been doing it every day all semester. The problem with that is we cannot give up 30 minutes a day for that. So maybe what it means is that I need to give like, I don't know, I can't force a person to study that way, you know? But maybe there's something I can do to help them. All right, off topic. I just want to make sure you did understand that I didn't think that you all like sucked at math. You know, it's like the test is not necessarily a reflection of what you're capable of. But the anxiety you get during tests, you got to get that under control. Because that's college. It's not my rules. Got to play by the rules though. Okay. Imagine if you took 2 tests a semester, 50% each. That's what it's really like when you get to your like junior, senior level courses. Midterm final, 50-50. You show up, you perform. And imagine if you took the entire half of our semester, right, 8 weeks, and imagine me giving you a test with 6 questions on it that somehow encompasses all that material. That means you have to know it all, right? I mean, like, because you don't know what 6 questions I'm going to ask you. That's what it's like when you start progressing into higher courses. All right, so, all right, what happened here? What's happening over here? Concave what? Up? Here? Okay, up? Okay, good. So we have, where's the inflection point? IP. So at f of negative root 4/3, we get, now did you get a decimal? It's okay if you got a decimal, but you had to plug that into here, right? Into the original function. So I don't mind plugging it in without decimals. Check this out. If we take that and we raise it to the 4th power, first we square it, which would give you 4/3. Then you square that, which would give you 16/9. Right? That's 4/3 squared. And then we have minus 8 times this squared, which was 4/3, and then plus 8.
Would it be negative 4/3?
We squared it though.
Squared, never mind.
So this would be 16/9 minus 32/3 plus 8. I know that sounds terrible, I'm sorry. I don't think I'm contagious. Common denominator. So I multiply the top and bottom here by 3, right? So I think that's 96 ninths, and then 3, so 24 ninths. See, I could do all, this is all just arithmetic, right? And then whatever that is. Someone have a decimal? Anyone have the decimal? No? All right, 16 minus 96 plus 21. I'm getting negative 6.2. Anyone else get that? Yeah. Okay. And here's some good news. If we plug in root 4/3 positive root 4/3, we're going to get the same answer because it's an even function. So I'm going to say this. How about this? I have 2 inflection points at plus and minus root 4/3, and they both come out to give me this. All right, I believe, what's step 8? 8's the table, Bobby table, right? All right, so here's the Bobby table. Here's what we're going to do. And the inspiration for this table is that when I was learning this, like I think I told you this before, this is just the way it made most sense to me. But it is just a slight adaptation of what's shown in most textbooks. All right, so here's what we're going to do. We're going to imagine that we're going to be putting a table up here, okay? And then directly below it, we're going to be putting the graph. Okay, so you have to make sure you have enough room for this wherever you are in your book. So I'm going to draw a number line here. This number line right here is going to be for my table. And then this number line right here is going to be for my graph. So imagine there's a y-axis down here, like this. Okay, so you see my graph here, and then this table that's going to come up here. All right, on this table, we're going to put our critical numbers from both the first and the second derivative. So what were the critical numbers from the first and second derivative? From the first derivative, they were 0, 2, and negative 2? Okay, so I'm going to put here 0. I'll put 2 out here. I'll put negative 2 right here. That means on my graph, line these up, 2, negative 2 down here like this, okay? And 0, of course. All right, what were the critical numbers from the second derivative? Positive and negative root, right? Root 4/3, which was 1.15. So I don't know, somewhere around here. Negative root 4/3, positive root 4/3. We don't have to get it perfect. We'll do the same thing down here. Okay. Now, here comes the table. What we're going to do with this up here is wherever we have these critical numbers, we're going to draw vertical lines, not dotted lines, just vertical lines like this. And then we're going to put horizontal lines that are going to create up here 3 rows. So watch. I have a first row here, and then a second row, and then I have a third row up there. You don't need this last line, but if you want to put it there, there it is. Can you see the distinct 3 rows here? Yes? Mm-hmm. All right. So the way that I've reasoned this out is as follows. What I'm going to put on each of these rows is going to be the information that I've already gathered about these derivatives in the first and second derivative. So this first row, I'm going to put information about the first derivative. The second row is going to be information about the second derivative. And the top row is going to be information about the function itself. So watch what I do. I'm going to go and take a look. Remember we did a number line earlier with test points for the first derivative, and we found out where it was going up and down. Let's look at that. We're going to be working on this first row. The numbers we had there were -2, 0, and 2, weren't they?
Yeah.
OK, to the left of -2, what was my function doing? To the left of -2. Was it going up or down? Down. So I'm going to put a down arrow here. OK? Then it switches. And from -2 to where does it go up? -2 to 0, right? So both of these are going to be filled in with ups. Understand? Then from 0 to 2, it's downs. Down, down. And then from 2 on, it's up. OK, see how I filled out that row? And all the columns are filled in? OK, now I'm going to go to the second derivative and use its information. And that tells me about concavity. So I think it was at -√4/3. To the left of that, it was up, right? So both of these are ups. And then from -√4/3 all the way to +√4/3, it's downs. So they both get downs. And then to the right of √4/3, it's ups. Now, to figure out what f is doing, what we do is we look to the left of -2. I must be a smile and going down, right? A smile and going down. So let me illustrate this. I must be a smile, but I must be going down. Well, this smile, if we cut it in half, if you're on this side, you would be coming down, wouldn't you? But on this side, you're going up. So it can't be the right side of this. It just has to be the left side of this. That means my overall function to the left of -2, my overall function must be looking like this over there. Does that make sense? Now what about this? In this column, you must be a smile, but you must be going up. Now it's the other half, okay? Now you must be going up a frown. So here's a frown, but you must be going up. So this side you're going up, this side you're going down. So we've got to be just the left side of that. Understand this? Sure? Yeah. Okay. So we got to be looking like this. And then we got to be coming down the frown. So the right side. Okay, we've got to be going down a smile. Which side of the smile? Left side of the smile. We've got to be going up a smile. Which side? Right side. Okay? If you look in books, the way that books do this is they use what are called sign charts. And they use they put here like negative, positive, positive, negative, negative, positive. Then they put positive, positive, negative, negative, positive, positive. And then to do this, they're just like, well, if you have a negative and a positive, you do that. It's just, it doesn't.
It's confusing.
Yeah, if you've ever seen it, it's like, what? And that's the way I looked at it when I was a student too. And I was like, well, wait a minute. I mean, this is all about the shape, right? So if you reason it this way, you're down a smile, you're on the left side, right? Okay. All right, now we get to put it all together. We got our table, and we get to do our graph. So here's our x and y axis. Everything lines up. So let's actually go in and start at the beginning. We had some x-intercepts, didn't we? All right, 2.6 and 1.1. So let's add some more detail to this. So here's, if this is maybe 1, this is 2, maybe this is 3 here. So 2.6, I actually have a point here, don't I? 2.6. And 1 point, what was this one again?
1.5.
1.15? Okay, so this is actually at 1.1. I don't know, just a little bit to the side of it, right? That's an x-intercept. And then it's on the other side, kind of like over here, and then a little bit inside of this. Those are my x-intercepts, yeah?
Yeah.
I also have a y-intercept of 8. So maybe I should count by 2s here. 2, 4, 6, 8. Put a dot there. So that's my graph, right? So far, these are points on my graph. What next? Why don't we, I'm going to change these to blue so you can tell the difference between the graph. What about our local max and local min? Didn't we have a local max? Where was our local max?
0 to 8.
0, you plugged in 0, it spit out 8, right? That's a local max. Okay, so I already have that one plotted. How about local minimums? It was at -8?
-8 and -2 and -2.
So at 2 and at -2, I'm down at -8. So if I go down 2, 4, 6, 8, there's -8. At 2, I have a point here, right? And then at -2, I have the same thing. All right? What about from the second derivative? Don't I have inflection points? So when we plugged in negative root 4/3, what did it spit out? Negative 6 point something? 6.2. So if this is -2, -4, -6, -6.2 would be somewhere around here. So I'm coming straight down from here to here, and then straight down from here to about the same place. Wow, I don't like this, but it is what it is. I kind of wish that my x-axis was stretched out a little more so that these points weren't so close to one another. But it is what it is at this point. Let's go with what we can go with. All right, I think we're ready. So let's start out, let's go off this table. -2, right? We had -2 here. And to the left of it, it had to look like this. So I'm going to go down to -2. There's a point. There's my point, right? Now to the left of this way, it has to look like this. So it's going to go like this. It's going to come up through this point. And then what is it going to do? It's going to go to infinity. And that matches with what the left-hand behavior was. So I'm actually going to fill this in right now with the left-hand side of a smile. Like that. Now, between -2 and this root thing, I've got to look like this. So that means between these 2 points, it's got to look like this. Curve it in like that, right? Can you see that? Now here's where these points are so close together it's hard to see this. I'm going to erase this so you can. How about we exaggerate this a little bit? Take these little points and let's move them in just slightly in so that we can really kind of exaggerate what's happening here. Okay. Between where and where? Where am I at?
You're between 1 and 0.
See, look, I've got to go from here to 0, right? And I've got to look like this. But I've got to get through that point, right? Up to here. So I am going to be like this. That's kind of tight to get that in there. But do y'all see that looks like this? And then this is where it switches over. Yeah. Use pencil. And then it's going to be a carbon copy of itself on the other side. But let's use the table. From 0 to here, so from 0 to this point, it's got to look like that. Right? That one's pretty good. And then from that root to 2, it's got to look like this. I think this side's coming out better. And then to the right of 2, it's got to look like that and pass through that point. Oh, then I screwed it up. There it is. So again, there's a lot more detail here on this picture than there would be if you just typed this into a computer. Because we can identify the actual points, like we know what that lowest point is. We also know where this inflection point occurs, right? Where that happens. All right, that was one problem.
1 hour
Let's do another one.
Can we see on business?
You want to see this one? There it is. See? Right here. Where's the inflection point? Might be hard to see it here, right? But again, this is about a process. This is about, can you do this very long process where you have to actually bring a lot of different things together here. Right? You're taking derivatives, multiple derivatives. You're setting them equal to 0, which means you're solving equations. You're taking limits, right? You have to do some limits, and then you have to do a lot of just kind of analysis of what's going on and keeping track of what you're trying to accomplish, and multi-step problem. All right, let's go with something with a little more oomph to it. This one just looks interesting to me. Now that is not a function that you've ever been asked to graph before, right?
Maybe just the square root part.
Yeah, maybe just the root, but not with this minus x here. All right, let's go. First part, domain. Domain is not clear. It's not obvious. Because we can't take roots of negative numbers, right? So what we need to make sure is that x squared plus x is always greater than or equal to 0. And that is called a quadratic inequality. I was talking to one of my colleagues the other day who's teaching 1414, and she asked me, should I emphasize this at all? I said, yes, absolutely. Because they get to calculus and I say, this is a quadratic inequality, and then they're not sure what to do with it. So you remember what the process is for something to solve that? It's okay if you don't. First thing you do is you switch it into an equation, all right? And you solve that equation. So I can factor an x out. I get two solutions, 0 and negative 1. So if I plug in 0, if I plug in 0 or negative 1, I'm going to get 0, which is OK. The question is, what about all the other numbers? So here's where you do a little number line. And this is not we're not looking at the derivative and testing. That's not this completely separate idea. This is how we solve quadratic inequalities. It's very similar, though. We do test points. But just don't confuse this with the derivative. We're not messing with the derivative right now. And we plug some points in, and we try and see when we get bigger than 0. So let's plug in like negative 2. Let's plug in negative 1/2. And we can plug in 1. There's an easy way to do this. Can anyone tell me the easier way to do this? You want to know when this is bigger than or equal to 0, right? That's what you want to know? OK, that is a parabola. Which way does it open? Up, right? It opens up. Where does it hit the x-axis? What are its x-intercepts? 0, negative 1, right? So imagine if I graphed this parabola. These would be the x-intercepts. And the parabola would go like this, wouldn't it? That's what the graph of this little piece right there would look like. So we're asking, when is it bigger than 0? which means where is it above the x-axis? So isn't this graph above the x-axis over here and over here? Yes? And below the x-axis here. So it's going to spit out negative numbers if you're between -1 and 0. So without doing test points, I could actually figure this out by just knowing the x-intercepts and knowing if it opens up or down. So I'm going to go with the domain of this is -infinity to -1 unioned with 0 to infinity. When we graph this function, it will only, the graph will only exist to the left of -1 and to the right of 0. Is that clear? How I got that? Any questions on that at all? Step 2. Step 2. Step 2. X-intercepts. Oh, this ought to be fun. X-intercepts. To do that, you set the function equal to 0. I really like this problem. This is really a good problem. Let's bring it back, bringing it all back. You have to solve a quadratic inequality. And now you have to solve a radical equation, a square root equation. So let's see if we can remember the technique to solve this equation. The standard process is to isolate the root. Okay, get the root part by itself first. So move the x to the other side. And then, once you isolate the root, you square both sides. So if I square the left, I get x squared plus x equals x squared. And now, you can minus an x squared on both sides. And you get x is what? 0. So you only have one solution here. Now, I have to check this solution though. And that's because anytime you solve a square root equation, when you square both sides, you introduce the possibility of extraneous solutions. So we have to double check it. So let's double check this. If I do 0, 0, 0, is that true? Yes, so that checks. OK. So I have one x-intercept. So my domain was -infinity to -1 unioned with, nobody asked me why there were brackets on the -1 and on the 0. Are y'all OK with the idea that you can actually plug those in and get 0 and that it's defined because you can still take the square root of 0? OK. And then the x-intercepts, there's only one. That's making me happy. x0. How about the y-intercept? This one should be easy. Oh, it's the same as the x-intercept. Look at that. Right? If we plug 0 in, we get 0. So the origin, right? The origin, 0, that point 0, 0, is part of our graph. All right, what about even odd? There's one way you can eliminate the possibility of this being even odd right now just by looking. That x squared is even, isn't it? And that right there is odd. And they're mixed together. And so there's no way it could be both even and odd. But you could also use the idea that, look, we don't even have a continuous graph. Like it breaks off. So how could it be a reflection of itself if the domains are all out of whack? You know what I'm saying? So even, odd. So symmetry, you're going to put none. Step 4, which is up or down?
Oh, no, the asymptotes.
Asymptotes. OK, yeah. I was like forgetting something here. So OK, vertical. Do we have any division by 0? Do we have fractions? No. So we're not going to have vertical asymptotes if we don't have fraction. What about horizontal? OK, well, to do that, we have to do two limits, don't we? Let's do them one at a time. Let's do the limit as x goes to infinity. Oh, this is going to be nice. Oh, yeah.